Okay, let's do implicit differentiation. Now that I think about it, maybe I'm thinking that I did some of these already because I did some similar examples for my business calculus videos, so maybe that's what it is. So if you heard me say in the first video that it seems like I may have already done these, then maybe that's what it was. Okay, but now let's talk about implicit differentiation. So we want to find dy over dx here. So what I'm going to do is I have e to the xy, and I want to apply the derivative to that, and then I have plus x squared, so I want to apply the derivative to that, and then I have minus y squared, so I'm going to apply the derivative to that, and then of course apply the derivative to 10. So I'm going to apply the derivative with respect to x to each of those. Well, e to the xy, I have to treat that like e to the u. And so the derivative of e to the u, remember, is e to the u times the derivative of u. So I have to multiply by the derivative of xy. Now remember, I have to assume y is a function of x. So when I get the derivative of xy, I've got to use the product rule. So I have x times y prime plus y times the derivative of x, which is 1. And then, of course, the derivative of x squared is 2x. Since I'm differentiating with respect to x, I can just say that's 2x. And then for the derivative of y squared, I have to use the general power rule, so I have 2y y prime. And then, of course, the derivative of 10 is 0. Now, I'm going to go ahead and distribute the e to the xy here. So I get e to the xy times xy prime, and then e to the xy times y. And then now, remember, with implicit differentiation, we want to look for the two terms that have, or the terms that have the y prime in them, which actually are these two terms. So I'm going to keep those two terms on the left, and then I'm going to move these two terms on the other side. So let's move these two terms on the other side, and they'll change to minus. Okay, now I probably should have put in another step here, but let's see if you can follow. Pretend like you've got these two terms together, and that's all you have on the left. Well, now you can factor a y prime out of each of these terms. And if you factor a y prime out here, you get x e to the xy, and if you factor a y prime out of here, you get minus 2y. So I get y prime times x e to the xy minus 2y. Now, if you divide this factor into this factor, you get your final answer. Now, I thought it might be interesting. I actually put this in a graphing utility and got the graph, and so you can see, you know, it's kind of got an interesting graph. It's kind of got an interesting bump right here and right here. So, you know, those are some interesting little bumps there, probably where the derivative is not defined at those values. Okay, now let's go over here and let's do one involving a trig function. So here I'm going to apply the derivative with respect to x to both sides. Well, the derivative of e to the x cubed with respect to x, since that's a function of x, then I can just do explicit differentiation. So the derivative of e to the x cubed would simply be e to the x cubed times the derivative of x cubed, which is 3x squared. Now here I have to treat this as sine of u. So the derivative of sine u, remember, is what? It's cosine u, and then you multiply by the derivative of u. So I've got to multiply by the derivative of x squared y. Now, how do I find the derivative of x squared y with respect to x? I have to use the product rule. So I take x squared times the derivative of y, so that'd be y prime, plus the derivative of x squared, which is 2x, and then times y. So that's the product rule. Now, I'm going to go ahead and distribute over here, and I'm going to get x squared y prime times this cosine. So I get x squared y prime times that cosine. And then I get 2xy times that cosine. Okay, now let's isolate this x squared y prime cosine, because it has the y prime. It's the only term with the y prime. So let's isolate it over here, and then I'll move this term to the left. And so over here I'll get 3x squared e to the x cubed minus 2xy cosine x squared y. and that equals this, x squared y prime cosine x squared y. So basically, if I divide x squared, see, I have this factor and this factor. So if I divide those two factors into the left-hand side, it'll just leave me with the y prime. So that's all I did. So I just took what I had on the left and I divided by x squared over cosine x squared y. And that gave me the derivative of that. So there's the implicit derivative of this. And notice that this has this kind of a funky looking function here as well. So anyway, you can kind of see it looks like we're getting a lot of vertical tangent lines here. Not sure exactly where they are, but remember, any values that makes the denominator 0 would actually give you vertical tangent lines. Okay, here's an application involving exponential functions. A store sells blankets made of Australian wool. They sell X blankets at P dollars per blanket, and so here's your price function that's called the demand equation. So there's your price function. So where X is the number of blankets, so based on the number of blankets they sell, the price is going to be 350 times e to that negative 0.001x. So it says find the rate of change. Rate of change, that's important because that means the derivative. So find the rate of change with respect to demand when the demand is 800 blankets. So now what I need to find the derivative of this with respect to x. Alright, so let's think about that. The derivative of that with respect to x. Well, the 350 would just stay there, the constant. And then I would have to find the derivative of this. Okay, so well, the derivative of e to the u, remember, what is it? It's e to the u, which would be this, and then it's times the derivative of u. So I'd have to multiply by the derivative of the exponent, which would just be the constant negative 0.001. And then when I multiply this constant times the 350, I actually get negative 0.35 e to the negative 0.001x. And then, so if we want to know the rate of change, so the rate of change when x is 800, then we plug 800 in for x in this function. And you can see that when you plug 800 in for x and plug, I just did this with a calculator, I got negative 16 cents, negative $0.16. The second question says, how much should the store charge to maximize revenue? Well, remember, revenue is x times p. So let me give that to you because I didn't give that to you just yet. Okay, so revenue, remember, is x times price. So we know price is 350 times e to the negative 0.001x. So if I rearrange this product, you can say it's 350x times this, and then you can actually use since we want to maximize this function, you can use the product rule to actually find the derivative of this. And then when you find the derivative of this, you can actually factor out the negative e to the negative 0.001x out, and what you'll get is 350 minus 0.35x. And then you can set that equal to 0, and the only way this can equal 0 is if that expression equals 0. So all you have to do is solve this linear equation and just move the 0.35x to the right, so then you divide 0.35 into 350 to get x, and so x is 1,000 blankets. So now so if you to make sure that actually does give you a maximum, you can use the first derivative test to show that you get a maximum. Then the price, it says how much should the store charge. So this doesn't tell me how much the store charges. This just tells me how many blankets the store needs to sell to maximize revenue. So to get the price, I have to take this 1,000 and plug it back into the price function. So I actually get 350 times e to the negative 0.001 times 1,000. and that gives me $128.76. So that's the price that should be charged in order to maximize revenue. So price $128.76, and then 1,000 blankets, and there you go. Okay, here's another example. It says when a telephone wire is hung between two poles, the wire forms what's called a catenary. This function actually can represent the equation of the wire that's hanging between the two poles, where it runs from -30 to 30. So they're going to be 60 feet apart. So we want to show that the lowest point is actually the middle. So what we can do is we can take the derivative of this. Pretty simple. Remember, the derivative of this would be 30 times the derivative of this. Well, if you take the derivative of this, let me show you what's going to. So if you take the derivative of the top here, you're going to, the 30 constant is going to stay outside right here. But when you take the derivative of e to the x over 60, remember you're going to get e to the x over 60, and then times the derivative of x over 60. Well, that's just 1/60th times x. So what's the derivative of 1/60th times x? It's just 1/60th, right? And then the next term, you're going to get the derivative of this is going to be e to the negative x over 60 times the derivative of negative x over 60. Well, likewise, the derivative of negative x over 60 is negative 1 over 60. Now then you can factor 1 over 60 out of both terms, and then that'll give you 30 over 60 outside, which reduces to 1/2. So you actually get 1/2 times this expression. And then of course, in order for this to let's see what I want to do. I want to minimize that, right? So in order to minimize the height, I need to set it equal to 0 so that I can find the critical numbers. Well, if you set it equal to 0, the only way it can equal 0 is if these two guys are equal to one another. And the only way these two guys can be equal to one another is if their two exponents are equal to one another. And the only way that x over 60 can equal minus x over 60 is if x equals negative x. Now I just used common sense and I said the only number that equals its opposite is 0. So therefore the minimum must occur where x is 0. Now another way you could solve this is to just move the minus x over, and you're going to get 2x equals 0. So if you don't like the way I did it, you can do it like that. And then obviously you just say 2 times what is 0, so x has to be 0. So either way, you're going to get x equals 0. And so here's a picture of it. Of course, this is where x equals 0, and this is x equal minus 30 over here. And of course, x equal 30 over here. And then you can see you get the minimum here. It didn't ask for the minimum, it just said where would you get a minimum, or it just said show that the lowest point is midway between the two poles, and obviously 0 is midway between negative 30 and 30. Okay, so that pretty much covers your derivatives of exponential functions. And now I want to talk about derivatives of other bases. So I'm going to kind of switch places here and talk about derivatives of other bases in the next video.